Hello everyone and welcome to We Meet at Digital Days. My name is Lisa Richter and I will moderate this presentation. We are very pleased that you took the time to participate in our virtual conference. The topic of this presentation is ER LEDs or VCSEL, when and where to use them. Our speaker is Dr. Celio Andreev. He will present the presentation and will answer your questions. Before we start, I would like to point out one thing. You will be muted during the presentation. This means that you cannot ask questions during the presentation, but nevertheless, you have the opportunity to ask questions during the presentation at any time via the chat function. You will find the chat function in the control panel. This presentation will be about 30 minutes long, and the chat questions will be answered in a Q&A session following the webinar. There are 5 to 10 minutes in addition scheduled for this. If we are unable to answer all of your questions within this time, we will answer them via email afterwards. If you still have any other questions left, just mail us at exhibition@we-online.com. We will try to answer all of your questions promptly. At the end of the webinar, you will be asked to participate in a feedback survey. We would be pleased if you take the time to fill out a survey and help us to improve our event. You will receive the link to the presentation in the next few days, and the recording will be available at our website shortly. So now I will hand over to our speaker and I wish you an exciting presentation.
So, hello everybody, and thanks Lisa for the nice introduction. Welcome everybody to the presentation. Today, just a few moments before we finish everything. Now I hope that you can see the screen in the correct mode, and I would like to welcome you to our presentation about the infrared LEDs or VCSELs, when and where to use them, and what type of application and specifics we have for the product. So I would like first to start with a short overview of today's talk. First, we will do a short introduction of the VCSEL and infrared LED technology, the differences, and what you can expect from it, short basics. Then I will give you a basic application guidelines or what type of applications we have in this case, and then finish with some examples for what the product can be used and what type of information is there to be looked for. I will finish with a short overview of our product portfolio, and then we can go to a question and answer session. But first, let's start with some technology introduction. What we mean by technology introduction? The first thing is what are infrared LEDs and what is a VCSEL? An infrared LED is a light emitting diode. I think this technology is more or less known for everybody. Infrared light emitting diodes are on the market for more than 60 years. On the other hand, the VCSEL, the vertical cavity surface emitting laser, is a rather new technology that is getting developed more and more in the late 20 years since it started. It's a type of laser emitter that emits vertically and not edge emitting or horizontally. It allows very small size emitters and coupling multiple emitters on a chip, but for this I will go further. The main differences between the light emitting diode and the VCSEL are the type of emission. For the LEDs, we have the spontaneous emission output, and in comparison, the stimulated emission allows a higher power output, a higher driving current, and a higher power output. For light emitting diodes, where we have maximum output of around 1 watt, VCSEL can go up to 4 or 5 watts. The difference also is in the wavelength. Wavelength 850 and 940 nanometers are the typical infrared wavelength emissions. The difference is that light emitting diode is based on the recombination, spontaneous recombination of carriers in the semiconductor, so it has a rather large bandwidth of around 40 to 50 nanometer spectral width, while the VCSEL, on the other hand, has a spectral width of around 2 to 5 nanometers due to the resonator, built-up resonator, and the amplification of the light into the active carrier. This also gives more effect on the switching times due to the amplification and the structure. We have switching times of nanoseconds, less than 1 nanosecond, while for the infrared LEDs, the switching time or the turn on off time can range in up below 10 nanoseconds. It's very hard to achieve such time, so we have more or less tens of nanoseconds or hundreds of nanoseconds for the good infrared LED design. The other differences is the beam output. We have a very high divergence or spreading of the beam. Infrared LEDs, because the chip emits from all its surfaces, we have usually the chip emission of 180 degrees. For the LED package, 120 degrees in the normal case, and we can change this with secondary optics. On the other hand, for the VCSEL, we have a very low beam divergence because of the output. In design itself, the LEDs and the VCSEL structure design doesn't differ. As you can see, the main components here, just a moment, the main components are also based on the substrate or the package. Then we have, of course, the difference is either the chip, infrared chip, or in our package we use the state-of-the-art VCSEL array chip with multiple gold bonding and multiple single VCSELs on it for our higher output. Of course, the different housing, this is specific for every component. The most important thing here is we have here the design of one high power LED and a high power VCSEL. This is the ceramic substrate with low thermal resistivity for decreased temperature effects in the product. And of course, at the end, we can build up different type of optics for different beam conversion and for different forming of the output. Of course, by the VCSEL, we usually use diffuse silica glass to modify the small beam or output. And this is also what we want to show here, the difference in the emission pattern. As you can see here on the left, we have the emission pattern of a single LED. It looks like a point source, and you can see the typical Lambertian effect or Lambertian emitter on the polar coordinate, where we have this polar circle. Or in Cartesian coordinates, we have this steady slope seen also on the pattern emission on at a surface at a distance. On the other hand, a VCSEL has a more homogeneous pattern with a bigger flat surface where we have a homogeneous emission and then steady or very steep flanks and no emission on the surface, or more or less looking like this 3D pattern. These two different patterns can be used for different applications. and can be used depending on what one needs to achieve. With this, I would like to go to the next topic and show a bit more about the application details, or what type of applications we have, and where we can use the VCSEL and the infrared LEDs. For this, I decided to focus on a brand new or a very hot topic in current days, and this is the 3D sensing for different ambient recognition and autonomous applications. In these applications, one needs to know and to understand in 3 dimensions the ambient environment, or what is happening where. You may have seen this more in autonomous driving cars and autonomous vehicles. I think this would not only be connected to autonomous vehicles, but it can be used in a lot of different ways. And here I summarized a few of the main models to do the 3D sensing. The first one is called structured light modeling. It uses a complex emitter system that emits a pattern light design. When this pattern line design is illuminated on a surface, then depending on the surface, we can have different changes in the design, in the pattern. Then using a camera, we can detect the picture, the pattern, and through a complex computation, we can estimate the 3D form of the objects that are surrounding us. It's a rather complex system, but it can use infrared LEDs and then some pattern design or some secondary optics for different patterns. On the other hand, with the VCSEL systems, we have a choice of 2 other different models. This is called the time of flight, or TOF designs. Here we have 2 different models again, the direct and indirect time of flight. What is time of flight? Time of flight usually uses the speed of light and emission and detection of light, and how much time is needed for the light to go and to come back from an object, to measure the distance. As we can see, by direct time of flight, we use a short pulse which is sent out from the emitter. It would be reflected from an object and returned to the detector. Measuring the time difference between the emitter and detector, we can measure the different distance between emitter and detector. The indirect time of flight, on the other side, uses a pulse train or from the emitter, and then compares the phase shift or the delay into this detector. As you can see, detector 1 needs to detect the emission light directly at the emitter, and detector 2 can detect the light after it returns. And using this phase shift, one can measure the time delay. But to get more details about the 2 different time of flight models. Okay, I hope that you can still hear me very good, because the system complains that I have a slow network connection. I will just ignore it and keep on going. The difference between the 2 time of flight models, or TOF models. The direct time of flight is a rather simple model that uses a very fast detector in the form of avalanche photodiode, or single photon avalanche diode. It can get a very fast acquisition. It has a very good precision, as it's able to distinguish between different reflections or different light sources. It has a very good signal to noise ratio, and it can have a great range in new systems where you can modify the emitter. You can go up to 200 meters or more. The benefit, those are the benefits, and what actually is the drawback is it has a reduced pixel detection and it uses a large data volume for the computation and for the estimation of the signal. On the other hand, the indirect time of flight, it can use a multiple detector system with multiple pixel counts, and it has a longer integration time, but it uses fast detection, and it can have a bigger resolution. Unfortunately, you'll see this on the next slide. It has a lower detection range, and it is not that good defining different shadows and reflections. To better understand this, I have also included two of the main components here, or how the time of flight is working. One of them is so-called scanning leader system, where we have a single ray output and we have a scanning mirror which rotates and sends beams in each direction. Then the detector can detect each of the beams from each of the detections, and with this scanning and moving, we can have a whole picture of the whole system. It's used for a wide range of detections. It's a very simple and precise solution, and it can have a very wide range because it can use a single beam with a low divergence and high output power and lower time for detection, and mostly applicable for the direct time of flight model. On the other side, we have the flash leader system, where we have an emitter like the emission pattern that I presented to you, where we can illuminate the whole scene with a single flash. And then we use an image sensor with multiple pixels, or a CCT sensor matrix, where we can detect the whole scene. The benefit of this system is that it doesn't use any moving parts and it can detect the whole scene. It has a simple construction but rather lower range, up to 20-30 meters in most cases, mainly due to the output power of the leader and due to the possibility to have a different pose train or the phase shift. Of course, mostly used in the eiSos system. Then basically how we can use this working on the LDD, on the laser driver. We are in the process of developing a laser driver system where we use components or the cooperation with Mindset. I hope you have seen the presentation 2 days ago for their GAN driver, MDC901. And using our Würth Elektronik VCSEL package, we are working on a system that can give different train poses or single poses systems. And we are still ongoing development, and soon it will be available as reference design for different TOF and LIDAR applications. I hope that this was now enough overview for what we are using our 3D sensing systems, or what's the difference between different laser and VCSELs. And now I would like to go more into direct application and show you in which applications we can use lasers or VCSEL systems. And first, I would start with a very familiar topic. This is biometric measurement. Biometrics is more or less health monitoring systems or measuring the biorhythms of the body, where we have different pulse measurements, oximetry or the blood oxygen measurement, and we find such parts in different wearable devices like smartwatches, sport systems, different uh, smart wearable devices, and of course in different sport devices or different fitness tools and different home tools for measurement. What type of LEDs or parts we use here? Uh, in most cases here we use our low power, mid power infrared LEDs in the form of chip LEDs, top LEDs, PLCC LEDs, and detectors. On the other hand, compared to the biometrics, we can put biometrics also into a different group, which is the biometric recognition group. Here we focus more on recognition of different uh, persons or different yeah, access controls and security systems. And here we have two different ways to do this with the face recognition solution or hand recognition solution. As we know, each person has his own face structure or eye structure, and what biologists have found out that people have different vein or blood vessel pattern in their hands. Here we can define the different products, for example, face recognition, where we have the iris scanning or 2D face recognition, uh, where we can use this with infrared LEDs, and we have a series of high power LEDs which can help this, or 3D face recognition, where mostly applicable are the VCSEL systems in the way of indirect time of flight, for example. On the other hand, we also have the hand recognition solutions where we have the fingerprint scanning with different low power LED solution, or the vein pattern scanning where we need a more in-depth view on the hand, and high power LEDs. Except recognition, more application where we can use infrared LEDs, for example, are different contactless and safe hygiene systems, for example, also in different toiletries and in such times where more or less we are talking about personal hygiene, washing hands, and uh, trying to go more and more into the open and use uh, different office buildings. Such touchless systems can help increase our hygiene. In addition, we can see in every house there is a remote control or smoke detectors which use the diffraction of infrared light for detection of smoke or uh, free air. In this case, we usually use also the low power LEDs as PLCC or chip LEDs or the standard through-hole technology. Uh, Further application fields is different smart home devices, security and night camera observation, where we can use our high power products for night vision and observation of our private sphere at night. But nevertheless, we can also use a lot of different type of detectors in our house for presence and sunlight detectors, where we can also decrease the energy consumption and have different turn on and off times of the LEDs, or use sunlight more effective in our house with putting the shades up and down when sunlight is directly detected. Up to now, we talked a lot about infrared LEDs detections, and now here is our view of the VCSEL application or the time of flight applications. Uh, we see this more at the moment into the industry area, where we can have different production or automated productions, and use it for different robots or different product monitoring system. And of course, worker safety systems where the autonomous devices can see the ambient around them and they can interact in a very fast way. When there are obstacles, they can also perform tasks in a more faster and accurate way, and also uh, benefit from this application. What I even heard in the last time is that people want to use this type of application also in the gardening or automated gardening. For example, automatic mowers or robots that are picking up fruit automated in the gardens where they can recognize the size, the form, and the position of the fruit, and such different applications where devices need to be more autonomous. With this, I would like now to go to our short introduction to our product portfolio, as the time is also running low. And first of all, our laser product, the new series VCSEL with emission wavelength of 940 nanometer, soon coming also the 850 nanometer with radiant flux of 2 watts and different viewing angles. X stock available 60 by 45 degrees and 110 by 85 degrees light emission pattern field of view. In addition, we have a very broad range of infrared LEDs, which we build up in the time with 850 and 940 nanometer available wavelengths and field of view between 20 and 150 degrees. We have a wide range of chip LEDs with all possible uh, soldering pads or footprints. We have also the standard PLCC type of LEDs, and of course our high power ceramic series with single and dual junction, so with uh, output power more than 1 watt. In addition, we offer a wide range of photodiodes with the standard chip and through-hole technology side, with black and white lens for daylight filtering and standard detection, and of course our phototransistor portfolio with matching footprint to our low power infrared LEDs, again with and without daylight filter and different size and forms. For more information, you can always contact your sales representative and get a contact with us so that we can help you further. With this, I would like to thank you for your attention, and I'm now open for some discussion or questions that you might have. Thanks a lot, and looking forward for a nice discussion, and if not, wishing you a very nice day.
Thank you, Celio, for your interesting presentation. Like you already mentioned, we will now have a look at your questions. So you can just write us a question via the chat function in the control panel, and then we can check it. So a first question. You have in your portfolio the package of 3535 for VCSEL. Are also some other packages are planned?
So thanks a lot for the question. At the moment, we are looking for this type of VCSEL, the 3535 size as a standard footprint. Further packages we are looking also for, and in this case, it is possible to make further different packages. When and where they are going to come as official product, we are not sure, as we are still looking into how to develop the product portfolio. But if you have any inquiries or you need any support, you're always welcome to contact us, and we can find the solution for you.
Okay, thank you. Another question, is it possible to combine infrared LEDs only with photodiode or also phototransistors?
Infrared LEDs you can combine with photodiodes or phototransistors depending on the type of applications you need. For example, the difference here is between the photodiodes and phototransistors, their response time and their signal level. Photodiodes are a simple on-off device with a very short switching time in the range of a few nanoseconds and very low output current of a few microamperes. On the other hand, phototransistors are a transistor type device. They benefit on the transistor gain, so they have a higher signal output in the range of milliamperes, sorry, but they have relative lower and slower reaction time in the range of microseconds. But you can always combine them with both of them.
Okay, great. So if there are no other questions left, I think I will say thank you at this point here, and we can finish the presentation. If there are still other questions, write us a mail at exhibition@we-online.com. Thank you very much for your attention, and I hope you enjoyed our presentation. The next presentation topic is bypass mesh from concept to prototyping. The presentation starts at 1 p.m. See you there and enjoy our digital days. Goodbye.
Bye bye.